Hi, this video will be an introduction to FETs or field effect transistors, specifically MOSFETs or metal oxide semiconductor field effect transistors. MOSFETs are, in the simplest terms, voltage controlled switches, meaning a change in voltage on one terminal switches the device on or off. MOSFETs have similar characteristics to BJTs, which are current controlled switches. If you'd like to know more about them, there is a link in the description. In this circuit, I have a 10 volt supply and a 5 volt supply, as well as an N-channel MOSFET over here, some resistors and a switch. And as I flick the switch, you'll see the circuit begins to conduct current, about 5 milliamps. As I flick the switch off, you'll see the circuit stops conducting current. In this way, we're using the N-channel MOSFET as a switch, which is controlled by the voltage on this pin here. This is known as the gate pin, similar to the base pin of a BJT if you're more familiar with them. We will come back to this circuit in a minute. First, let's look closer at what's going on inside a MOSFET. An N-channel MOSFET has 3 pins. G, the gate pin over here, this is the control pin. D, the drain, this pin connects to your load, so it could be a resistor. And S, the source, this pin connects to ground. When the gate pin is high, the resistance between the drain and the source becomes very low, which allows current to flow through it. When the gate pin is low, or 0, the resistance between the drain and the source becomes very high, and no current is allowed to flow, or almost no current, as no component in the real world is perfect. You might notice that the MOSFET symbol here looks slightly different to the simulated symbol. This is merely a quirk of the simulator I'm using. They are in fact the same component. Now let's look back at our circuit and go over it with some more detail. This resistor at the top is acting as our circuit's load, so it decides the current that passes through the MOSFET when the MOSFET allows it. This resistor here is a safety feature. Even though by design MOSFETs never allow any current to flow through the gate, sometimes as a MOSFET is switching between on or off, a small amount of current can flow. This resistor here limits that. And then finally, this resistor is what is known as a pull-down resistor, in that it pulls down to ground. This allows the current flowing out of this gate supply to go somewhere. MOSFETs also have what is known as a voltage threshold. This is the absolute minimum voltage required on the gate terminal in order to make the MOSFET switch. On this particular MOSFET, the voltage threshold is 1 volt. This means that once the gate supply over here goes over 1 volt, the MOSFET will begin to allow current to flow. If I set the supplied voltage over here all the way down to say half a volt, so below that 1 volt threshold, you'll notice no current flows, even though the supply is connected. If I set this all the way up to say 2 volts, you can see that current begins to flow as it's now over that 1 volt threshold. Now before I continue onwards to the P-channel MOSFET, there is one more thing I need to mention. In this MOSFET, as we know, the voltage threshold is 1 volt. So if I set the gate source to say 3 volts, current flows and we get 1.7 milliamps. If I then increase the gate source up to say 5 volts, we now get 5.8 milliamps passing through, so a considerably higher value. This is because MOSFETs have a changing response as the gate voltage increases. This might look confusing at first, but carefully look at this graph. This is just an example graph of a nondescript real-world MOSFET. Now the most important thing is seeing that for any value of VGS, so the gate to source voltage that's noted by each of these different lines, there is a different maximum current that can be reached. Now this might seem confusing at first. I often struggle interpreting graphs, but if we now look back at our previous circuit, we can prove it. If I set the gate voltage back down to 2 volts, as we saw before, we get 400 microamps. If I set it up to say 5 volts, as we saw before, the drain current being allowed through the MOSFET goes up to 5.8 milliamps. This simulation corresponds well with our previous graph. Now there is one other type of common MOSFET, and that is the P-channel MOSFET. This circuit uses the same components as our previous, only in different positions. The key difference is that our gate supply, over here, is the other way around, with the negative side connected to the MOSFET gate terminal. This is because this MOSFET needs a negative voltage of at least 1 volt on its gate compared to its source to function. But nonetheless, if I open the switch, you can see that current begins to flow. 5 milliamps is being allowed through the MOSFET at 5 volts, and if I increase the gate supply to say 7 volts, we now get 7 milliamps passing through. If I then close the switch again, current ceases to flow. Let's now look at what's going on inside a P-channel MOSFET. A P-channel MOSFET has the same terminal names as an N-channel, only it operates differently. On a P-channel, you still want to have the gate be your control pin, only you want less voltage on the gate than the source, instead of the other way around for an N-channel. On a P-channel, you would typically put your load after the MOSFET instead of before it. Now looking back at our previous circuit, all the resistors perform the same role as they did in the previous circuit, except, as mentioned, our load is now after the MOSFET down here, and the gate resistor is now a pull up instead of a pull down, meaning it pulls the current up to the supply, so the gate current has somewhere to go. Before we finish the video, there is one more thing I need to mention. For this video so far, I have been showing you what are known as Enhancement Mosfets. This means they turn on when you go over their voltage threshold. You can also get depletion MOSFETs, which turn on when you go under their voltage threshold. Thanks for watching. Be sure to like the video if you liked it, subscribe if you loved it. Have a good day. See ya.